Hi everyone. So welcome to this video on trees, which are a special type of graphs that contain no cycles. Okay, so let's define trees first. As I just mentioned, a tree is a simple connected graph that contains no cycles. Note that it has to be a connected graph for it to be a tree. Well, if you drop the connectedness condition, then it's called a forest. Right? Any graph that contains no cycles is a forest. So as you see in these examples here, this is a tree, right? It's connected and it has no cycles. The second graph is not a tree, right? This is not connected. It has two connected components, one with 4 vertices and one with 2. The third graph here is connected, but it has a cycle, right? So it's not a tree. And trees have surprisingly a lot of applications. For instance, if you've taken a computer science course or two, then you might have seen binary search trees, or you might have used trees as a data structure, right, in your code. We're not going to go into the details of these algorithms, but as you can see from the structure here, since there are no cycles, well, anytime you want to model something that has some kind of hierarchical structure, then trees might be useful for that kind of scenario. So what I'm going to do here is to prove a first property about trees, which is the fact that if you start with any tree on any number of vertices, and if you remove one edge from that tree, then the resulting graph will be disconnected. Okay, and now if you look at these examples, so I look at the first example here, you can see that that result is true. I can remove any edge. I can remove that one, and that disconnects the graph. I can remove this one, that disconnects the graph. It gives me the second graph. I can remove this one, that also disconnects the graph. I'll have one vertex alone as a connected component. So how would we prove that? How would we show that you're always going to get something disconnected? So here's how we'll prove it. And I'll just note here that this notation here, G minus E, is the same thing as saying G, well, it's the graph obtained by keeping the same vertex set, but from your edge set, you're removing E. Right? So if you call E the edge UV, then it's the same as saying remove the edge UV. Right? So sometimes we'll refer to edges just with a name, just call the edge E. Sometimes we'll refer to them using their endpoints. So it's the edge from U to V. So here we actually give names to the endpoints, U and V, to the edge that we're removing. So what do we have here? So we say, so let G be a tree, and E an edge in the tree connecting U and V. And let's remove E. And we want to show G minus E is disconnected. Okay, so let's do this by contradiction here. Since the negation of what we want to prove here is to say, we'll assume it is still connected. Right, so we want to use this to get a contradiction. Okay, so what goes wrong in this scenario? So just imagine, right? You have some graph whatever, and say that's U and that's V. This is the edge E in your graph. Okay, so I'll make it different color here. That's E. This is the whole graph G. If we delete the edge E, boom, we remove it, right? But then the graph remains connected. What does that mean for us? Well, it means there is still some way for us to get from U to V in the graph using a path. Right? Maybe it looks like this, maybe it goes around somewhere and then goes back to V. Right? So in this graph, after we delete E, there was still a UV path because of the definition of connectedness. Well, how is that a contradiction? Well, that means in the original graph, when E was still there, that means you had a cycle. Right? And that contradicts the fact that G was a tree to begin with. Okay, so how would we write that down? So assume G minus E is connected. Then, by definition of connectedness, there's a UV path in G minus E. Okay. But this UV path is also in the original graph. Right? Because all that differs between G and G minus E is the deletion of that edge E. So, therefore, we add E to that UV path. And it gives us a cycle in the original graph. And that's your contradiction. Contradicting the assumption, or let's just say contradicting that G was a tree to begin with. Right, so that's nice. That tells us, okay, well, given any tree, remove an edge, it will always be disconnected. And in a sense, what this tells us is that trees are the minimally connected graphs. Minimally connected. Right? In the sense that they're, in some sense, the smallest kinds of graphs that remain connected. So you remove anything from them, connection disappears, right? They become disconnected. And this will come up in some of our other proofs when we characterize trees. Now, another result, another property of trees is that trees have leaves. That sounds silly when you say it out loud, right? But that's how these graph theory definitions go. A leaf in a tree is what we'll call any vertex with degree 1. So if you look at like a tree in real life, right, the leaves are kind of at the ends of your branches. And that's the same thing for graphs. The leaves in this tree on this slide are these vertices. And it is true that any tree, in the sense of graph theory, has at least 2 leaves, or 2 vertices of degree 1. Okay, so try it yourself. Try drawing any tree. You'll always get at least 2 leaves. Right? In fact, path gives you exactly 2 leaves. But as soon as you start adding branches, you're going to get more. right? Because you can't ever connect these guys to get a cycle. So how would you prove this statement? Well, I won't go through the entire proof here, but I'll give you an idea. The proof uses maximal paths. What is a maximal path? As the name suggests, it's a path in your graph so it's a path in the graph that can't be extended to become longer. Okay, what does that mean? So for instance, this path is maximal, right? Because these are your endpoints, and there's no way for you to connect any more vertices to this path to make it longer. So right now it's a path with 4 edges, right? And note that the word maximal here does not mean that it's the longest path, right? It's maximal in the sense of containment. But if you look at this graph, well, for sure there are longer paths. I can do this instead. And that's a path with 6 edges, which is also maximal. And now to prove this result, you're just going to have to say, well, take a maximal path and argue that the 2 endpoints of a maximal path are leaves. Right? Assuming we're in a tree, of course. And yeah, I guess I'll just leave you with that and let you try that yourselves. And I'll give you a hint here. Maybe contradiction works? What happens if you form some maximal path and they're not leaves at the endpoints? What cases happen there? Right? What can happen? And how does this give you a contradiction?